In this short video, we will look at surface tension, which exists at liquid-liquid and liquid-vapor or liquid air interfaces. So if you look at the liquid contained in this container, a particle in the center, liquid particle in the center of the container is attracted to other liquid particles in all directions. However, if you look at a particle close to the surface, it is attracted to liquid particles on the inside, but there are no liquid particles on the other side with the similar attractive forces, which leads to a net inward attraction of this liquid particle towards the bulk liquid, which creates a tension at the interface. This is for a liquid vapor interface. If, on the other hand, you have a liquid interface such as oil and water, then this surface tension arises from the difference in the intermolecular forces near the interface. So this water drop or water particle will experience forces differently from oil than would this water drop or water particle, which experiences intermolecular forces only from other water particles. So this is the molecular basis for what is called the surface tension. Another way to understand is that liquids minimize their surface area and become spheres because of this tension. To quantify this, think of pulling off a liquid film. So let's say you have a liquid in this container here, and then you take some sort of a wire and you pull the liquid in this direction. Now there are two films for the liquid. One is on this side and the other is on this side. And if the length of the liquid film is L, then the total amount of film is equal to 2L. And it was found that the force needed to pull this liquid film in this direction is proportional to the length of the liquid film, or the force is equal to the surface tension, which is the proportionality constant, multiplied by twice the length of the wire. Now if the liquid film moves by a distance dx, then the work done is equal to the force, which is 2 times the surface tension multiplied by the length multiplied by dx. And if you divide this by the area is nothing but twice the length multiplied by dx. This is equal to the surface tension. Or in other words, since this is differential work is equal to the surface tension multiplied by a differential change in the area. This is very similar to expansion work that we have talked about earlier. This surface tension gives rise to what is called the Laplace law, which essentially states that at a curved interface of radius r, the pressure on the concave side is higher than the pressure on the convex side by 2 times the surface tension divided by r. So if you have a liquid droplet or if you have a soap bubble, there is a difference in the pressure inside and outside, and the pressure inside is equal to the pressure outside plus 2 times the surface tension divided by r. And this becomes very relevant when we are going to discuss lung surfactants in one of the exercises in the future. This difference is also the reason why you need energy to make smaller spheres compared to a larger sphere. Laplace's law gives rise to what is known as capillary action, which amongst other things is responsible for the rise of nutrients in plants and trees along thin capillaries. To understand this, think of a liquid container. into which you have inserted a small capillary or a tube of radius r. So the radius of this tube is equal to r. As the liquid starts to wet the capillary, it forms, in most cases, a concave interface. The formation of this concave interface implies that the pressure just below the interface is less than the pressure above the interface. So if the atmospheric pressure is P here, the pressure here is P minus 2 times the surface tension divided by R. This is the pressure at point 2. Because of this pressure differential, the liquid is pushed up, or the meniscus is pushed up, and the liquid keeps rising, let's say up to this point, until the height of the liquid in the capillary is h. The pressure right below the interface is equal to P minus 2 times gamma by R. But the pressure here now is equal to P minus 2 times gamma by R plus the hydrostatic pressure of the liquid in the column, which is equal to the density of the liquid, the gravitational constant multiplied by the height. At equilibrium, the pressure here at this point will be equal to the pressure here. So the liquid will not rise or fall any further. And therefore P equals P minus 2 times surface tension by R plus rho GH. Here rho is the density of the liquid. If you rearrange this, you can measure the surface tension, and this will be equal to the radius of the capillary, the density of the liquid, the gravitational constant, R divided by 2. If again you rearrange this, you can see that the height is proportional to the inverse of the radius of the tube. So the smaller the tube that is inserted into the liquid, the higher the liquid will rise. You probably have all experienced this in the lab when you use thin pipette, or of course we observe this every day when liquids or plant nutrients move up a stem in a plant. So this is a little bit about capillary action. So where is surface tension relevant in biology? It is important for any mechanism related to increase or decrease in the surface area of a membrane, budding or fusion, because a membrane also has a surface tension. This is inside the cell, this is outside the cell, and the membrane is essentially a layer of oil between a water layer here and the water layer outside. So there is a surface tension associated with the plasma membrane. So here are some examples. The first is endocytosis, where a membrane vesicle is pinched off the plasma membrane, and this depends on the surface tension in the membrane. Another example is cytoskeletal remodeling. When the membrane tension is low, then several filopodia or lamellipodia can be formed because it does not take a lot of energy to deform the membrane. Remember, the energy needed to deform the membrane is proportional to the surface tension. If, however, the surface tension is high, then a single lamellipodium will form, like this here. So the cell can control the number of lamellipodia and its movement in one direction based on actin remodeling near the membrane in this region and also the tension in the membrane. Another example is the entry of a virus, which also depends on, in this case, endocytosis, and therefore the tension in the membrane. Another example where membrane fusion and surface tension is important is synaptic vesicle fusion. Most of you are aware that in a synapse, a synaptic vesicle carrying neurotransmitter fuses with the membrane here to release the neurotransmitter into the synaptic space here, and this fusion of the vesicle into the synaptic membrane, or the membrane of this axon here, depends on the tension in the membrane. There are several other examples. that you can read in a review paper or in literature. Another example which you will encounter in your exercise is the human respiratory system. So when you inhale air or oxygen, it eventually ends up in these alveoli, which are really small. Um, we can approximate them as spheres, and I think they're of the radius of micrometers. And therefore, the pressure inside is much higher than the pressure outside, leading to a large pressure differential, and it takes a lot of energy for the alveolus to expand or to compress. This energy is reduced by the formation of what is called a lung surfactant layer, which you can see here, which is composed of lipids, which act as a surfactant to reduce the surface tension and allow us to breathe without expenditure of a large amount of energy. So these are some examples of the importance of surface tension in living systems. Another example that you can look at is this movie of water striders, which you can look up on YouTube using this link. So this was a short video about surface tension and capillary action. This is not present in either of your textbooks, and I will upload a small document that you can read from a different textbook to understand more about this and also the derivation of Laplace's law.